standing waves are a very particular type of interference between waves that produce a very particular sort of pattern in the wave. Standing waves are used in instruments. Whenever a musical sound is played, it's producing a standing wave somehow, either on a string or in a tube, depending on what kind of instrument is being played. Again, the string is the easiest example to deal with. So let's consider we've got a string, and let's say both ends of the string are anchored to a wall or something, so that these ends don't move, right? So if you pluck this string, odds are good that it will vibrate with these ends won't move, and it'll vibrate so that it creates this sort of half wavelength. It'll go back and forth between being up and down, and it'll hit everywhere in between, but it's just vibrating back and forth in this sort of wave shape, which is why it's called a standing wave. There are these points of zero displacement called nodes that are not moving. Again, if you vibrate the string in a certain way, you could create another type of standing wave where you have a full wavelength, and there's also this node in the middle. So like if you have your string, the first picture is just the case where you pluck it and the string is going, just going back and forth like that. Whereas the second case, there's also a node in the middle, and the string is doing something more like this, where it's the two ends are vibrating, these two sides are vibrating back and forth, but the middle of the string is holding still. And it creates this pattern of nodes, and then these places of maximum displacement are called antinodes. And you can keep going and get a wavelength and a half. I didn't draw that very well. Or two full wavelengths, and so on and so forth. And these are called harmonics. This is called the fundamental or first harmonic, and then they're just given numbers. This is the second harmonic, this is the third, fourth, and on and on. And you could have an infinite number of harmonics. Okay. So the first harmonic the wavelength, whatever is the length of this string here, the wavelength is twice that. For the second harmonic, the wavelength is equal to that length. For the third harmonic, this is 1.5 wavelengths, and so the wavelength is equal to, well, the wavelength is from here to like here, that's 2/3 of our length. Actually, it's easier to go the other way. Let's say in this case the wavelength, or the length of the string is half the wavelength. In this case, the length of the string is the wavelength. Here the length of the string is 3/2 of a wavelength, and so on and so forth. You can see the pattern. These are just half multiples of our wavelength. So the length of our string then is equal to lambda to n over 2, where n is 1, 2, whatever. It's the number of the wavelength. And we also know that v equals lambda f, so we can replace this lambda with v over f, and therefore say that our length equals vn over 2f, and therefore the frequency of each of these harmonics, if we solve for that, is Vn over 2L. Again, where n equals 0, 1, 2, or sorry, just 1, 2, etc. And this is the equation for the harmonics, or the places where the standing waves occur. Note that this two features. This frequency is inversely related to frequency varies inversely with the length, which is why, like on a piano, lower strings are longer strings. The longer strings produce lower sound. This is why a cello or a bass is lower than a viola or a violin, because they have longer strings. Okay. We also know that frequency is proportional to velocity, and remember the velocity of a wave in a string is proportional to the square root of the tension in the string, which is, tuning a stringed instrument. You either tighten or loosen the string. You tighten it to get a higher pitch, you loosen it to get a lower pitch. So when you tune a guitar or violin or cello or any sort of stringed instrument, that's what you're tightening or loosening the string. That's much easier. You can't really change the length of the instrument on the fly, but you can tighten or loosen the strings to change the pitch of the string. And that's also on stringed instruments when you're fingering. What you're doing is changing the length of the string, and therefore changing the frequency of sound that it will naturally produce. You can similarly produce standing waves in a tube. And this is what happens if you've ever, I don't know if you've ever done this, if you just get a pop bottle and you blow over the top of it, it makes a sound. This is also how any of your wind instruments are going to work, or like a pipe organ. In a closed tube, the wave created is such that this end is anchored. It's a node. We have a node at the closed end of the tube and an antinode at the open end of the tube. Right? That's just how they're created. So this first harmonic, the length of our tube, well, this is from 0 to max, and then we need to go down to 0, min, 0. So this is only a quarter of a wavelength. Now if this end is a node and this end is an antinode, it skips what would look like our first harmonic for a string. It skips this thing because this has nodes at both ends, and instead, so we skip over that second possible pattern, and we get something where, again, we have an antinode at the end, so it looks something like this, where the length of the tube then, this isn't quite a full wavelength, it's in fact 3/4 of a wavelength. Continuing on with the pattern, we can see that our length, it's equal to n lambda over 4, but n is only odd numbers. Okay, and following the same pattern, if we substitute in b over f for our frequency, then we can say that the frequency of the nth harmonic is just nb over 4l, where n, again, is odd. This is something we're going to use for our lab. We're going to see where we produce resonance. But anyway, so for a closed tube, we can see there are only odd harmonics. If it's an open tube, if the tube is open at both ends, you have antinodes at both ends, then you can do all the same. It's kind of the opposite of the case of the string, but you can do a full wavelength, you can do half a wavelength, and so you have the half wavelength stuff. So this result we got for string, this is for a string. It's also the case for an open tube. Tube that's open at both ends. Whereas this case where only the odd harmonics exist is the case for a tube that is closed at both ends. Or, sorry, closed at one end. As humans, we hear sounds best at about 3,500 hertz and 11,000 hertz. And the reason for that, i.e. these are the easiest sounds to hear, is because these are the first and second harmonics of our ear canal. So sounds at this frequency are the ones we're most, around those frequencies are we're most able to hear. I looked it up, 3,500 hertz is between A6 and A7, which apparently should mean something to music people. It doesn't mean anything to me, but that I guess could help you out if you know what A6 and A7 are. Yeah. Another phenomenon that has to do with interference, as I briefly mentioned before, is what are called beats. So this is when we have two sources or more with different frequencies. Then they're creating, you're creating multiple sine waves and cosine waves. And so the loudness kind of fluctuates because if you have, so for example, if you have a sine wave that looks like this, and you're overlapping that with a sine wave that looks like this, they're going to add, but then they're at different points. They might have destructive interference at some places, and they might have constructive interference at other places, and the wave's going to be all goofy. The important thing that you need to know, well, what winds up happening when you add them together is that it looks something like this, where you'll have there'll be an oscillation, and then there'll be like one big wave, and it'll oscillate back and forth and then spike at different places in the wave function, depending on how they work together. And the frequency of these maximum points is called the beat frequency. And the beat frequency is just the difference in the two frequencies, absolute value. And that is, where the frequency of when you hear those extra loud parts of that. There's a nice little graph in your book, I forget what page it's on, that shows how that plays out. And I'll also show you, again, as I said in class with tuning forks, I'll show you what that, I'll let you hear what that sounds like.